So you will remember that we had a second relationship with water waves. And that was where we were looking at a point where there was a node, in other words, where there was destructive interference, and we were relating a whole bunch of things together. The distance between the two sources, the distance from the point between the two sources out to the node, the wavelength, and as well the distance from the center line to the position of the node. And so we had related all those things. We actually did it by relating them to the sine of the angle. And so we were looking at comparing the opposite and the adjacent and using the fact that, oops, this angle and this angle were the same. Okay, believe it or not, water waves and light waves, pretty much the same thing. So same relationship holds. Okay, this is the distance from the center line to the first dark fringe where you're getting destructive interference. This is the distance from the two slits in this case, which act as sources that are in phase with each other. And this is the length. Sorry, I probably already said that. Now, this is for destructive interference. In other words, this path length is out by, just like it says, lambda by 2, or potentially when we go over to the next dark fringe, 3 lambda by 2. It's always out by some multiple of half a wavelength. Sorry, yeah, integer plus a half a wavelength. Okay, now, for constructive interference, in other words, if we're going from the central maximum to another bright fringe here, all we really have to realize is that that path length difference, denoted by this opposite side of the triangle, is now a wavelength, or potentially 2 wavelengths, or 3 wavelengths. And so we just change this to n lambda over d. No different than before. And we can rearrange it if we like. xnd equals n lambda l. The textbook we're using actually uses m to denote distance to a bright fringe. Other than that, everything is pretty much exactly the same.